Hello everyone and welcome to today's webinar titled Monitoring Downstream Purification with Raman Spectroscopy using the ProSelect Raman Analyzer, hosted by Biopharma Webinars and presented today by Greg Voiter, who's Senior Engineer Upstream Process Development Manager at Merck. So firstly, hello Greg, welcome. Thank you for joining me today. It's a pleasure to have you here. And then we are also joined by Dr. Kim Nguyen, who is Senior Scientist, ADC Bioconjugation Template Innovation at Merck. So, Dr. Kim, hello, welcome. Thank you for joining us as well. It's a pleasure to have you here. And then last but not least, we have Alexander Faris, who is Bioprocessing Engineer at Merck. So, Alex, hello, welcome. Thank you for joining me today. It's great to have all of you here today. So my name is Marcus. I'll be today's moderator. And before we begin, I'd just like to inform our viewers that there will be a live question and answer session after all three presentations today. So please feel free to send in as many questions as you'd like during this webinar via the questions button located directly below your webinar screen. And then I will ask these questions to Greg, Kim, and Alex during the Q&A session. And please also state in your questions which presenter you would like me to ask your question to. Now, please allow me to introduce our first presenter. So Greg Voiter is a senior engineer, part of the upstream process development team at Merck. His team supports process development and scale up of upstream technologies, and his focus areas are cell retention systems and PAT technologies. Greg has over a decade of experience in the biotech industry, with previous roles in downstream MSAT and extensive experience in the virus filtration unit operation. Greg holds a bachelor's degree in chemical engineering from Worcester Polytechnic Institute. And with that, I'd like to hand over to our first presenter today. So welcome, Greg.
Thank you, Marcus, for the time. So today I'm going to be talking about, I'm going to be providing an overview for our next presenters and providing some background around Raman spectroscopy and tangential flow filtration and how we see that combined offering being of value when monitoring downstream purification. So just as a forward, the life science business of Merck KGaA, Darmstadt, Germany, it operates as Millipore-Sigma in the US and Canada. So you may hear me say Millipore-Sigma in some of these cases. I am based in the US, but just if you're part of the global audience, know that I'm referring to Merck. So my content for today will be broken up into three sections. I'll be giving first a background on Raman spectroscopy. Next, I'll be giving an overview of tangential flow filtration at a high level, and then be talking briefly about the benefits of integrating Raman spectroscopy in TFF before passing it off to our next presenters, who will be giving a more in-depth look at their specific unit operation and step of interest. So to provide an overview on Raman spectroscopy, when we're looking at Raman spectroscopy, we see it as a valuable PA2 tool for measuring a variety of different components in line. So you can see it here connected to a bioreactor or a tank, being able to measure components like metabolites, your protein titer, your cell densities, your solvent levels in line, measuring several process parameters simultaneously. In that process, it's outputting real-time analytics, which you can then use to communicate to your process controls and make real-time decisions about your process. It's also worth mentioning that the reason Raman is selected is because of its excellent selectivity to be able to measure different peaks of different components at the same time. And it's a laser that is non-destructive, so it can be used in solution without having significant impact on your product quality. So all these time and resource savings make Raman a good tool for a variety of different conditions in unit operations. So when we're looking at how at a high level the system functions, first we are emitting a laser, which is housed in our unit, going all the way through the probe body into the probe tube, where it's emitting a laser into your solution. The built-in analyzer is then picking up that Raman signal and communicating it back to our software. Then the software, based off the chemometric models that are built, are making real-time decisions and calculating and displaying real-time values of the components that you're interested in measuring. When we look at Raman spectroscopy at a high level, we are a laser is being emitted and applied to a sample, which is creating a few different types of collisions. So there's a Rayleigh's collision, which is a collision that results in no net change of energy, so it does not contain significant useful information. So when we're looking at the Raman shift, we are filtering out that Rayleigh's elastic collisions and are focusing instead on the inelastic collisions, because those energy shifts from the vibrational effects of the molecule create a specific molecular fingerprint for each component in solution. Now, to give an example of that, we have a water molecule. So when a laser is exciting the water molecule, we're seeing multiple different types of bends and stretches that are occurring. And those specific bends and stretches are correlated to specific portions of the Raman shift. Now, the amount of energy, the net change of energy can be measured on that Raman shift as displayed on the graph on the right. So you can see that the specific components have different intensities, but overall they are all being measured independently. It's a significant intensity for water and the specific molecular fingerprint. So if we're just measuring water or a single component, it might be easy to clearly define the concentration. So we have just cyclohexane on the left here. You can see there are very sharp, clear peaks that in between the specific peaks of interest, there's almost no background interference. But when we're looking at a more complex media, like on the right, you'll see that there's a significant amount of background all across the Raman shift associated with a number of different types of molecules and their vibrations. So when you're dealing with complex medium, like we are dealing with in bioprocessing throughout most of our process, it can be difficult to differentiate them just by visually looking at the spectra. So that's why chemometric analysis is a necessary step to implementing Raman spectroscopy. So what you're doing when you're building your initial model is you are taking Raman spectra from inline monitoring of your process and correlating the specific peak intensities and Raman shift with offline analytics. So whatever offline parameters or analytics you're using to measure the component you're interested in measuring in line with Raman spectroscopy, you would take multiple samples and build a model around that specific component based off the Raman spectra that you've taken correlated with the specific sample points. And that correlation is compiled in a partial least squared model to create an additional calibration batch. Then once you have your chemometric model implemented, the model is going to take new Raman shift that is collected in real time in your process and convert the Raman shift to display real-time values for all the components that you're interested in measuring. So when we're looking at the different types of components that are measured, there's a wide variety of unit operations, applications across different modalities where we see Raman spectroscopy as benefits. Traditionally, it was used in the upstream space for measuring a variety of different components in a bioreactor, but we're going to be focusing today on the different downstream approaches, specifically around tangential flow filtration. We'll be looking at protein concentrations and solvent levels. So when we're looking at our specific offering, we feel we are positioned to meet some of the challenges of the space. So there's a number of different qualities of the system that we feel position us to implement well in tangential flow filtration. First, we have a number of different interlock systems and safeties built in to prevent any accidental exposure to the laser hazard. It's a small, compact system that's designed to be can be moved into a manufacturing space without additional enclosures being needed. It has a long optical cable, which gives you flexibility and placement and ease of use, whether trying to put it in a PD lab or in a larger manufacturing space. And then it has threaded connections that allow for easy connection to a standard probe tube threaded connection, as well as the probe tube, which is going to be the component of the Raman probe that's in contact with your product, being compatible with CIP, SFP, and autoclave sterilization. We also have a number of new additions to our hardware and software offering that we feel are increasing our differentiated offering. So on the left, we have our external measurement unit, which is a valuable tool when you're trying to build initial models. You can build initial models without expending a lot of volume using this external measurement unit, looking at sample volumes of less than 0.5 ml at a time. We also have advanced stray light features, both a hardware and a software feature with the light reducer cap, as well as additional noise reduction filters, which allow you to measure Raman signal without concern for stray light contaminating your signal. So if you have a large reactor, you don't have to worry about how do I prevent the Raman probe from being exposed to stray light. Then from a software perspective, we have a number of different tools built into our standard software offering that allow you to do to refine your data in a number of different ways. Here you see the effective pre-processing, where we're looking at the raw data and we're standardizing it, normalizing it, and also selecting specific regions of interest and accentuating the variance in them to give you a much clearer picture of how the different portions of the spectra affect the specific concentration changes of the component of interest you're trying to measure. We also have tools to perform PCA, principal component analysis, or PLS, partial least squared analysis, to further refine and understand your process. So looking at batch variability, looking at measuring outliers, and just an easy tool to compare all your data, which is all available with the standard offering that we have. So those are some of the, as we see, some of the main benefits of using Procelix and Raman spectroscopy. Now I'm going to provide a bit of a background on tangential flow filtration, or TFF. So when we're looking at filtration in general, it's going to be a pressure-driven separation across the membrane of liquid, usually based off a number of different parameters, but traditionally based off size exclusion. So traditionally, one of the main methods was normal flow filtration, where you basically are retaining any particle that's larger than the pore size of your membrane, and anything smaller is passing through. But we're going to be focusing on tangential flow filtration. So the tangential flow filtration functions in a different way, where we're measuring, where we're controlling the cross flow across the membrane. So it's also called cross flow filtration, and we're flowing tangentially to the filter surface. So as opposed to normal flow, where all the flow is going directly against the membrane, we only, in this case, have a small percentage of total fluid flow going through the filter medium, with a significant portion of that cross flow being retained by the membrane and being returned to whatever tank or vessel you are storing it in. When we sort of zoom in on the membrane, we see that the major driver of force is going to be that liquid tangential flow. And the separation across the membrane is still going to be pressure driven, but it's going to be a much lower percentage of that total flow. That flow which is going through the membrane, we call our permeate or filtrate flux. And that parameter is key when optimizing your process. Determining your filtrate rate flux is normally the first step when doing initial exploratory analysis and optimization, and can help determine how long your process may take, what your effective throughput is, what your effective conversion rate is. So there's a number of benefits optimizing that filtrate rate flux. And when we're looking at applications where tangential flow filtration can be of value, there's a number of different things, but we can narrow it down to the majority falling into 3 categories. First would be clarification, where your product is passing through the membrane, then larger debris is being retained by. Second would be concentration, where your product is being retained by the membrane this time, and solvent is passing through. And in this case, you're going to be decreasing the working volume or the total volume of your tank and increasing the concentration of your drug product of interest. Third is diafiltration, where we also see product retained by the membrane, and you're also passing buffer through. But in this case, you're also adding new solvent to your tank and changing the buffer medium that your product is in. So there's multiple reasons to do that. There could be an impurity in the initial buffer system the product is in. The new buffer system could increase the stability of your product, or it could make your product more compatible with it being injected into a patient, so be put into its final formulation. So when we look at digital filtration, there's a number of places in a process where you can use it. This is just a more traditional CHO process, or potentially a viral gene therapy process. And you can see any time where there's a need, where you see increased efficiency in your process by decreasing the working volume, exchanging the buffer. Tangential flow filtration is a potential place where there can be value. And we also see it across our products. One of the ones that can be broadly used across a wide variety of modalities. So whether if you're looking at a CHO process with a mAb or recombinant protein, looking at a plasma process, you're looking at a ATK process with AAV or lentivirus, or you're working on a vaccine or mRNA or LNP process, there is a solution that we can offer to optimize your process with tangential flow filtration. So now I'm just going to give a brief overview of the benefits of that integration of Raman spectroscopy with tangential flow filtration. When we look at some of the challenges of tangential flow filtration, we see that there can be issues with concentration shifts with UV sensors that lead to high saturation of signal. So you're not getting a good view of your high protein concentrations. There are aggregates that can go undetected, that can vary between batches that you don't have a way of seeing in real time. You can be trying to clear a solvent due to a variety of different reasons, but in some cases there's regulatory pressure to have certain ppm of a specific solvent. So there are issues with being able to optimize the process around that, or being able to tune a process to measure it consistently, as opposed to just using historical data. And then, as always, what we see with a lot of these steps, there can be a manual sampling burden, especially as you get closer to your final drug product. The risk of contamination becomes greater, and there's increased regulatory burden around any contamination. So how we see Raman being a fit to meet these challenges is it can measure proteins, excipients, and conjugates in line. It can also aggregates early, so you can tune it to measure aggregate levels as well. You can also tune it again to track solvents, so you can measure. You'll be learning about more of the specifics now in our next talk, and then it can be used across scales, all the way from PD to GMP and across a variety of different modalities. So we see overall, when implementing Raman spectroscopy in your TFF step, it leads to a higher quality process with reduced batch failures. You see efficiency in being able to monitor a variety of different components in line and making real-time decisions, as opposed to having to rely on historical data. And yeah, that real-time data acquisition and control can also lead to significant step gains, including potential yield improvements. So I'm just going to finish my portion of the presentation today with just an overview of what a tangential flow filtration process may look like when implementing Raman spectroscopy, where the placement may be, and just highlight that Raman spectroscopy is well positioned to perform real-time monitoring your critical quality attributes, and the ProCellEx offering can provide differentiated value for end users when trying to implement this step. So with that, I will pass it off to Kim. Thank you for the time.
Thank you very much, Greg. And a quick reminder before Kim begins. If you have any questions for Greg, please feel free to send in as many questions as you like via the questions tab found directly below your webinar screen. And then I will ask these questions to Greg during our live Q&A session after Alex's presentation. Okay, and now I'd just like to introduce our next presenter. So Dr. Kim Nguyen has been working in the company for 9 years, first in process and analytical development, then in innovation, focusing on analytical method development and optimization. Before she joined Merck, Dr. Nguyen had postdoctoral training at the Washington University in St. Louis, performing research to evaluate radiopharmaceuticals for diagnosis and treatment of cancers. Dr. Nguyen has over 10 years of experience in analytical R&D, project management, technology transfer to GMP manufacturing. So now please let me hand over to our next speaker. Welcome, Kim.
Thank you, Marcus, for the introductions. Good morning, good afternoon, good evening, everybody. So my presentation today will be ProCellEx Raman's analyzer for solvent clearance monitoring. So this is a disclaimer about our company. The life science business of Merck KGaA Darmstadt, Germany, operate as MilliporeSigma in the US and Canada. So the initiation of this project was to test the application of ProCellEx Raman's analyzer as a PAT for real-time monitoring. We use organic solvents such as DMSO and DMA to dissolve our drug linker. So we need to demonstrate that we can clear the solvent in the final product. We want to demonstrate that ProCellEx Raman's is a powerful PAT tool for monitoring residual solvent clearance during a TFF process. The benefit of real-time monitoring are to ensure that we have a complete and good solvent clearance. In addition, we are collecting the real-world solvent clearance data to help guiding us for future process. We are using our model ADC and spike in 7.5% DMSO. Before I go into the experimental design, I would like to give a brief overview of the ADC. People who have cancer usually need to undergo surgery and/or radiation chemotherapy. However, chemotherapy is very toxic. It has a lot of side effects. It kills cancer cells at the same time killing normal healthy cells. With ADC, antibody drug conjugate, we have an antibody that bind to a specific antigen that overexpress on tumor cell surface. And then we have a linker that link the antibody to the toxic payload. Like a lock and key concept, when ADC is injected into the body, the antibody bind to specific tumor-associated antigen, it get internalized, and then the toxic payload get released into the cell. For the ADC conjugation process, first we conjugate the drug linker to the antibody, and then it may undergo an optional chrome purification step, and then the TFF process to remove excess drug linker and impurity, and finally it is formulated. So this slide shows our experimental setup. The picture on the left shows our ProSelect Raman analyzer where data was collected. On the right, we use a custom switching valve to collect offline sample to measure reference value for model building at different time points without disrupting process. In addition, we have our Raman probe placed inside the retentate bottle, which allow us to monitor the solvent clearance during the TFF process. And as you can see, we wrap the retentate bottle with aluminum foil to prevent straight line. We also have the TFF system to remove residual solvent. So in this slide, on the top graph on the left is the full Raman spectrum that we collected during the DMSO clearance. The bottom graph on the left is the Raman spectrum with 4 different wavelength range. These are the signature peak of DMSO. As you know, for process monitoring, we are dealing with a very complicated matrix. So usually it's very difficult to only use a single Raman shift to monitor the process. We can either use a full spectrum or different selected wavelength range. Also, our company offers a single probe ProSelect Raman or 4-channel probe. You can see that in previous great presentation. So you can monitor 4 different reactions at the same time. Our ProSelect Raman also has a very strong embedded statistical software. With this software, you can do partial least square analysis. From this, you can build a model and use the model to predict the value few times. But for this experiment, our integration times is 30 seconds, 5 spectral average. We also collect the offline sample every 5 minutes, and then we ran these samples using our platform method, which allow us to quantify the amount of DMSO. So the finger on the left represent the DMSO concentration of the offline sample in microgram per mil. We are using the data from the first TFF to build the model. We do a reference association of the offline sample with the Raman spectrum to build the model. On the right are the data pre-processing parameter, where we selected 4 different wavelength range. We will use this model to monitor our second TFF process, which is in this next slide. So for the second TFF process, we use the same parameter as the first one. We also collect offline sample to compare with the predicted values. In this slide, the offline sample represented by the blue circle and the predicted concentration from the Prosilite is represented in the orange circle. The insert graph is the zoom in for sample at low concentration. The table on the right at the actual concentration of DMSO for the offline sample comparing to the predicted concentration. The concentration that was predicted by the Ramons are very comparable to the offline sample. However, the prediction accuracy is poor for concentration below 500 microgram per mil. DMSO is a class 3 solvent, and the ICH guideline limit for DMSOs is 5,000 ppm. According to ICH guidance, PDE stands for permitted daily exposure, would set a limit on how much of a specific contaminant can be present in a drug product based on its toxicity profile. To calculate the concentration limit in ppm, we take PDE, which is 50 mg per day, multiplied by a conversion factor of 1,000, divided by dose, which is 10 grams per day, which gives us 5,000 ppm. To calculate the practical limit, we normalize 5,000 ppm to API concentration. For example, if both drug substance has 20 mg per mil API, the practical DMSO limit is calculated as 5,000 ppm multiplied by 20 mg per mil divided by a conversion factor of 1,000, which gives you a concentration of 100 microgram per mil. For this application, we want to monitor DMSO concentration at low concentration. So what we did was we went back and we do data pre-processing. We keep standard normal variate SG derivative and selected wavelength range the same. But to build this new low concentration model, we only include data set at low range concentration from 1 to 599 microgram per mil. We then apply this new low concentration model and we play the second TFF monitoring data. The reference value of the offline sample concentration stay the same. But because we are using a new model, so the predicted concentration is different. The new model only includes data set at lower concentration. So the prediction accuracies for high concentrations is poor, but the accuracies is getting better, starting below 10,000 microgram per mil, and this is good until 30 microgram per mil. This optimized low concentration model was able to give good prediction accuracy below the practical limit of DMSO. Our company introduced live reduction probe at the end of last year. With this probe, we don't have to wrap the reaction vessels with aluminum foil, which is an advantage to use with our single-use reactor. Straight line might simply appear as additional peak throughout the process. These can overlap with specific Raman wavelength that you need to use for process inside, either masking that information or resulting in inaccurate model building or inaccurate conversion by the model into quantitative or qualitative data for understanding and decision making and potential automation. Additionally, straight line can result in saturation of the signal monitor by Raman's analyzer. This can result in total loss of the data on those areas where saturation occurs. Our line reduction probe include a line reducer cap on the tip, and the software include noise filter features. So we ran experiment to test the performance of the light reduction probe and the regular probe in light environment. We also measured the offline sample for comparison. We monitor glucose, lactase, and viable cell densities. For these three fingers, the pink trace represent regular probe data. The blue trace represent light reduction probe, and the green triangle is the offline measurement. For the regular probe, light interference distort the Raman spectrum would create big fluctuation in concentration for glucose and lactase. This data demonstrate that light reduction probe has much better performance compared to the regular probe in light environment, and its prediction value is comparable to offline measurement. In closing, PATs is the foundation for next generation ADC manufacturing, especially when quality by design and real-time release testing will be implemented. For ProSillic Raman's model building and monitoring DMSO clearance in TFF process, the model with full calibration set has poor accuracy at low concentration range, but we were able to optimize the model to obtain great accuracy at low concentration range, which has a limitation around 30 microgram per mil below the practical ICH limit of 100 microgram per mil. State of the art PAT is making quality by design, real-time release testing, and smart manufacturing become more realistic and practical. Finally, I would like to thank my team member for all their help and support. Chris, EE, Dale, Nick, Howard, and our manager, Gong Yao. I would also like to thank Lisa McDermott, the manager of process and analytical development. I would like to especially thank all the team members in digital and smart solutions, business operation, Patty, Johan, and Kevin, for their collaboration, for their feedback, and for their help. That's all I have. Thank you.
Thank you very much, Kim, for your presentation. And a quick reminder, we've had some questions come in already, but if you have any more questions for Kim or for Greg, then please continue to send in your questions via the questions button found directly below your webinar screen. I will then ask these questions during our live Q&A session. Okay, so once again, thank you, Kim. And now please allow me to introduce our next presenter, which is Alexander Faris, and he is currently a bioprocessing engineer on Merck's PAT and digital applications R&D team, where he focuses on advancing ProCellEx Raman analyzer applications in downstream processing. Prior to joining Merck, Alex built a strong foundation in the biopharmaceutical industry by working in GMP manufacturing of viral vectors at Thermo Fisher Scientific's CDMO and providing manufacturing and development support for various biologics projects at Bristol Myers Squibb. Alex holds a bachelor's in chemical engineering from the University of Massachusetts. And with that, please let me hand over to our next presenter. Welcome, Alex.
Thank you. I appreciate the introduction. As mentioned, my name is Alex Faris. And in this portion of our webinar, I'll be going over Raman implementation in a downstream application, focusing on inline protein quantification for highly concentrated drug substances. Again, just this disclaimer, the life science business of Merck KGaA Darmstadt, Germany operates as MilliporeSigma in the US and Canada, which is where I'm located. So the agenda for this topic will start with considerations for inline Raman spectroscopy and downstream processing. Then we will move into the model development workflow for concentrated protein quantification. And then finally, we'll look at a couple of case studies that display the capabilities of the developed models. The first thing I want to discuss are some considerations behind the implementation of inline monitoring for a downstream process. We have seen a growing focus on intensified production and integrated systems across biologics manufacturing, and with that comes a complementary need for real-time inline monitoring of product streams for effective process characterization and control. In this slide, I'm going to touch on some of the challenges with implementing inline PAT into downstream processes, specifically surrounding measurement time requirements in upstream versus downstream to support inline measurement capabilities. When looking at bioreactor cell culture processes, whether they're by fed batch or perfusion, the extended run times, which are normally on the order of days to weeks, allows for generous time gaps between sampling and analysis. In these cases where the measurement frequency doesn't need to be rapid, typical sample removal protocols for at-line or offline analysis a few times a day are effective. In context to inline PAT solutions, such as a Raman probe submerged in a bioreactor, the accuracy of the analysis can benefit from more averaging of spectral measurements, but this is at the cost of increases to the overall measurement time. The main point of this is that there is enough time throughout a bioreactor run that these longer measurement times can still allow for successful monitoring and control of process parameters. On the other hand, downstream purification of biologics involves operations that experience process changes much more rapidly, especially at smaller process development scales. This makes inline PAT implementation much more difficult due to the requirement for rapid measurement times. The way I like to help visualize these scenarios is with this idea from a publication by Rathore et al. Called the ease of implementation ratio, where the decision time relates to the typical time that is available to make a decision before moving to the next process step, and analytical time refers to the analysis time for a given analytical method. These figures from the table are somewhat arbitrary and primarily just serve as a visual representation of the concept I'm speaking to, rather than as actual data that covers all manufacturing processes. For example, the 10-hour decision time for cell culture reduction aligns with taking a few samples per day, whereas the decision time for a chromatography operation is much shorter due to the nature of component peaks of interest occurring over a brief period. From this, you can see that inline PAT for downstream operations demand lower measurement times in order to provide a feasible solution. These times likely need to be on the order of less than a minute to increase this ratio of decision and analytical time for easier implementation. Altogether, this lower analytical time or measurement time is a major consideration that was focused on in this work. The main driving factor for developing this high protein concentration use case for ramen was to address our team's internal challenges, which have also been similarly noted by customers. In the past, our team attempted to monitor protein concentration in a highly concentrated, purified process stream exiting a single pass TFF system as the final downstream step. This process can concentrate protein samples beyond 250 grams per liter. Currently, there are systems on the market that allow inline monitoring of this type of sample stream surrounding UFDF operations, specifically numerous UV-Vis solutions. However, we faced challenges with the UV instrument we were initially using. These challenges included flow rate dependence, which is shown in the plot where you can see drastic changes in the concentration reading from only slight disturbances in the flow rate. Also, the stability of readings was pretty poor at low flow rates that are typical for smaller process development scales. And we see limitations of the maximum concentration range due to the nature of the UV system's variable path length. This opened our eyes to develop inline ramen models to measure highly concentrated protein samples. From this work, we found that Procelix ramen system, coupled with the flow cell, which is shown on the side here, solved the challenges we faced with the UV-Vis system. And an initial model developed around a single protein species aligned very well with offline reference measurements, with minimal measurement changes when flow rates were changed drastically. Additionally, the ramen solution carries with it the flexible ability of having different implementation capabilities and multiple measurement channels all within the same system. So that provides obvious advantages over other PAT tools that are currently on the market. Now we'll get into the high protein concentration model development. In order to be a true comparison against UV-Vis methods that can generally be used regardless of MAB type, our initial question was whether ramen could accurately quantify and monitor protein concentration in highly concentrated samples, regardless of MAB type or the buffer background. Also, what would be the limits of this type of model? To answer this, the development process was based on three key objectives. One, assess the feasibility of creating a generic model that can be applied to different MAB-derived species. For this, calibration data was generated to include 3 MABs called A, B, and C, and 1 bispecific called D. These were all purified similarly with their purification process and formulated into the same buffer background to minimize the integration time. So I mentioned that in the previous comment that we want to try to drive down this integration time for downstream processes. The plot to the right shows the method for determining a suitable integration time that can cover the entire desired concentration range. The integration time needs to be high enough to generate a substantial enough signal at the lowest concentration, while also being short enough to not oversaturate the signal at the highest concentration in the range. in this work, we generated one model at 8-second integration time to show the maximum concentration range a model can span. And we did a second model at 4 seconds that highlights how integration time can be optimized for specific desired concentration ranges that may be based on specific customer needs or process needs. So with no averaging included in these models, these integration times represent the true time between measurements. And then lastly, we wanted to ensure low relative errors by optimizing data pre-processing to minimize the spectral variability. Diving a little bit deeper into the workflow of generating these models, we can look at these two process flow diagrams. First, we start with sample generation, which consisted of the 3 MABs and 1 bispecific protein in the same formulation background, each with separate samples spanned across the concentration range of about 15 to 250 grams per liter. Spectra for these samples were generated through this recirculation loop with a pump flow rate of 0.5 mils per minute. With this setup, we created the calibration data for the 8-second and 4-second integration time models separately. Also to note, due to a low holdup volume of only 200 microliters within this flow cell, the recirculation loop only required a few milliliters per sample, which is a benefit and makes the requirements for product generations much more manageable when trying to develop models like this. For offline analysis, we used ProA HPLC, and these values were inputted as reference measurements for the spectra. So all of this was then fed into our pre-processing and PLS modeling workflow, which is included in the Procelix Raman and Chemometric Expert software, where we can perform qualitative analysis by PCA and outlier management. Proper tuning of pre-processing parameters is vital for developing an accurate and robust model. And these model evaluation outputs are what we rely on during the model building process. The text is kind of small in the bottom of this diagram, but these outputs are RMSEC, which is the root mean square error of calibration, RMSEC-V, which is the root mean square error of cross-validation. The ratio between these two values is helpful for determining if there is any overfitting of a model occurring. We also have the RMSEP, which is the root mean square error of prediction, which measures prediction error of new unseen data, incorporating the differences between the model's predictions and the actual observed values. And in this case, a lower RMSEP value indicates a more accurate and reliable model. Relative error percentage can be derived from the RMSEP, and this represents the model's error as a percentage of actual measured values. So with all these considered, once the model evaluation outputs are optimized, the model can then be used for real-time monitoring. So the generic aspect of this work really came into effect during the pre-processing of the raw calibration spectra that was generated for each protein. As you can see, the raw spectra of the 4 protein types, all at very similar concentrations of about 170 to 180 grams per liter. The spectra exhibited substantial differences. But by applying certain pre-processing techniques and optimizing the parameters, the spectra saw much better alignment across the various protein types. In doing so, we were able to reduce unwanted spectral variation among samples of the same concentration and also enhance consistency and comparability between spectra representing the same material. So this kind of just describes the different forms of pre-processing that can go into these evaluations. As mentioned before, the key model evaluation outputs that help to characterize the model performance is the root mean square error prediction, which can also be converted into the relative error percentage. In these plots, the validation sets consist of spectra and reference measurement data that was generated independently and was not included in the original model calibration data, which allows us to examine the model's predictive capabilities on new data. The data on the left displays the error for the 8-second integration time model, which spans about 15 to 250 grams per liter. And the data on the right displays the error for the 4-second integration time model, which just focuses on the higher range, concentration range of about 100 to 250 grams per liter. And this was done for each MAB type. From the results, we're very pleased to report that for all MAB types, the relative error was less than 2.5%. This is definitely a fantastic start for us, especially with the idea that the more we continue to build on this model with the additional data points and calibration sets, the stronger this model performance can become. So now I'm going to jump into a couple case studies that we have. These case studies display the capabilities of the model built with an 8-second integration time. In this first case, a validation study was performed on just MAB-A using this recirculation setup. So looking at the picture over here, the recirculation reservoir starts with a MAB-A concentration of 220 grams per liter, an auxiliary pump added diluent buffer at a rate of 0.4 milliliters per minute until it reached a final concentration of 22.2 grams per liter. Based on the dilution rate, the concentration change over time was calculated and is represented by this dashed black line. While the recirculation loop pumped the MAB sample through the Raman flow cell, the Raman protein measurement data was generated and plotted here in green. As you can see from the plot, the overlays of the measured values and the calculated expected values is extremely accurate over the entire concentration range. This case study is a bit more interesting and truly demonstrates the model's generic capabilities. This system the setup of this run is somewhat similar, where a concentrated protein solution was diluted using buffer across the concentration range of 200 grams per liter to 1 gram per liter. However, the sample components consisted of a brand new IgG sample that was not included in any of the calibration data used to build the model. And the background buffer used was PBS instead of the formulation buffer the calibration samples contained. Additionally, this data was generated on a completely separate Procelix system that the model was transferred to. The Raman probe was fitted to an Optec flow cell instead of the flow cell that the calibration data was generated with. And the operating flow rate was 1 mil per minute, whereas the calibration sets were generated with a flow rate of 0.5 mils per minute. With all of these drastic changes to the protein type, sample conditions, and basically the complete system setup, the model still performed well with relative errors less than 5%, which is on pace with other technologies on the market. This demonstration of robust transferability and generic capabilities for measuring highly concentrated protein is a very promising step for developing ready-to-use models to be included with the Procelix system. In summary, the Procelix Raman has been able to produce promising results as a robust inline process monitoring tool in the downstream space, especially for measuring high concentrations of various proteins. Looking at our initial key objectives for this work, we successfully met all 3 conditions to achieve low prediction errors with acceptable measurement times over a wide concentration range, with the perks of having a single path length flow cell, minimal dependence on flow rate, and the ability to optimize measurement times based on process needs. We also demonstrated transferability to an unseen MAB and process setup with major changes, including the actual Procelix system, flow cell, flow rate, and background buffer. As we continue to improve this Raman capability, we aim to further expand the calibration data library, as well as generate transferability data by testing with new molecules and work streams, all which can be achieved with welcomed collaboration. So with that, I just wanted to thank everyone who was able to join in with us today, and then I guess open up the session for any questions that might be out there. Also, while we wait for that, I'll pull up this contact slide in the meantime. But yeah,
Okay.
I think that's it for me.
Thank you then, Alex, for your presentation there. And a quick reminder to our audience members, you can still send in your questions if you have any for Alex or for Kim or Greg via the questions button found directly below your webinar screen. Please also include in your questions the name of the presenter you would like me to ask the question to. Okay. Once again, thank you, Alex. And I'm going to bring us back onto cameras now, and then we'll take our first question. Okay. Very good. Welcome back, everyone. So this first question I'll ask to Greg says, have you tested other PAT techniques like FTIR? Ooh, I'm going to stop you there, Greg. You are on mute. Let me just... there you are. You are unmuted now. Let's try again. Still can't hear you. Is your microphone settings okay on your end? Yeah. And you can hear me okay, I assume, yeah. Yeah. Okay. Let's defer this question for now, just to Kim. And Greg, will come back to you. We'll just try to have a look at your microphone. Okay, Kim, would you like me to repeat the question, or did you get that okay?
I got the questions. Thank you. So we did test the FTIR before we acquired the Raman. FTIR is widely implemented in solid organic based API production, but not much in the wire-based API. And we are working with ADC. So Procelix Raman's analyzer, seem to be a better choice for us.
Okay, thank you very much, then, Kim, for that answer. And Alex, did you have anything you'd like to add to this answer?
I don't have much to add. I haven't used FTIR, so sorry.
No problem there. Greg, how are things looking at the moment? Are we able to hear you at the moment? No, we still can't hear you. That's okay. I'll send you a quick message in the co-presenter chat, and we'll come back to you for the next question, just so we can make use of the time here. Okay, sorry about this. Okay, let's go on to our next question. I'll ask this question to Alex. It says, could you give me more details on the Procelix Raman analyzer and its software package?
Yeah, sure. So the Procelix Raman software, there's two components to it. There's the Bio4C PAT Raman software, which is where you can set up your process runs. This is where you can generate calibration data. So once you have your setup, you can set up your integration time, your number of averaging. You can put your probe into sample however you want to implement it, whether it's in a bioreactor, in a surge vessel, or if it's just sort of offline standalone measurement like caps that also come with the probe. You can generate spectra. You obviously have to get your offline measurements through another means of analysis. But once you have your spectra and your offline references, you can combine those, and then you can pull those into the second software that comes as part of Procelix, which is the Chemometric Expert. And within this software is where you can do your qualitative analysis, your outlier management. You can also apply all those pre-processing techniques and parameter adjustment in that case. And then once you kind of get to a good point in the chemometric expert and export your model, you can then bring that model back into the original Bio4C Raman software. And this is where you're actually going to be able to open it, apply it to your probe on your system, and then actually monitor in real time. So the combination of those two helps you build models from scratch. There's also ready-to-use models that will be included in the Bio4C Raman software. So that would kind of bypass the need to generate your own specific models, and we'll be able to just do the real-time monitoring just from that initial Bio4C platform or software.
Okay, great. Thank you, Alex, for that answer. Greg was just rejoining. How's things at the moment, Greg? Are we able to hear you?
Can you hear me?
Yes, I can. Yeah, welcome back. Good. I'm glad we're able to fix that. Before you go on to our next question, Kim, was there anything you'd like to add to Alex's answer?
I think Alex gave a very good overview of how you use the Procelix Ramons to collect the data, and then the software help you, with all the data pre-processing, build a model. Then once you have the model, you can use it, put it back, and then apply the model to predict, the reaction real time.
Okay, thank you then, Kim. The next question here, I'll ask this question to Greg. It says, what is the biggest challenge for implementing Procelix Raman?
Yeah, I would say the biggest challenge, I think, is having a good, robust understanding of your process and the components that you're trying to measure, and being able to measure them accurately and taking relevant spectra. So that initial calibration phase. But our team has been doing that for a while now and has worked in dozens of processes all over the world. So we're well positioned to help facilitate that and make it easier for you to implement your first models and get started using Raman spectroscopy.
Great, thank you for the answer, Greg. Anything else that Alex would like to add to this answer?
Yeah, sure. I can add a little bit just from personal experience. One of the challenges in at least building the models from scratch is ensuring that your offline reference measurements and your analysis of those also has like a pretty good error. I mean, the actual model building aspect is kind of limited by how well you can reference those spectra with accurate offline data. So that's definitely been one of the main challenges, is just ensuring that those offline references are accurate. Also, kind of in some more complicated sample feeds where it's hard to separate individual components, there's like a little bit of sometimes overlap in the spectral ranges of the components. So differentiating that can also be somewhat of a challenge, and is definitely helpful if you can purify those specific components better. But there's ways to do that, and it's kind of, I guess, just goes with digging deeper into research and sort of more trial and error.
Great. Thank you then, Alex, for that answer. And Kim, is there anything you'd like to add before our next question?
Yes. So actually, our ProSelect Raman's analyzer is easy to implement, particularly with our, new introductions of the lie reduction probe. To implement, first, you need to build a specific model for the target chemical. Second, you also need to check if there is a potential interference exists in the solution. And then third, you need to check if your construct is not light sensitive for 785 nanometer, which is the Raman's excitation wavelength.
Okay. Thank you then, Kim. Right. Happy to move on to our next question then. I'll ask this question to Greg once again. It says, do you see potential for Raman spectroscopy used in pharmaceutical compounding spaces, potentially in the potency confirmation / release testing capacity? For batch compounding, this seems very feasible. For patient-specific compounding, it gets murkier.
Yeah, so we do see the Raman being used in other similar applications to do potency confirmation release testing confirmations. So we see a variety of different spaces. Just one example is our media manufacturing team will take small samples of each one of their medias after they've been formulated to log the spectra to track batch variability or changes over time. Yeah, and generally speaking, when you're working on a sort of N of 1 process that's fairly unique or a unique compounding process, it becomes more difficult to have the Raman probe be able to accurately measure it because you don't have previous references. So that's always something to keep in mind. How repeatable is this process? How much data do we have that we can create an initial calibration model with? That's all important when determining what the value of it can be for your process.
Thank you, Greg. Kim, is there anything you'd like to add to this answer as well?
I think ProSelect Raman will be a powerful tool for, real-time release testing. So, we are, testing different components. And then hopefully, in the future, we will bring that, to manufacturing. That's the goal.
Yep. Good. Thank you then, Kim. And Alex, is there anything you'd like to add to this question? Oh, we're going to stop you there. You are on mute.
Yeah, sorry. I don't have too much to add to that answer. I think Greg can cover that pretty well.
Yeah, great. Okay, then thank you then. This next question I'll ask to Alex next. It says, I'm not a Raman expert, so I apologize for my novice question. Some of the things you've shown today have been quite eye-opening. So if I have a Raman spectrometer set up in a well-lit room, there is a legitimate concern that my results are going to be poor, even if the sample is in an enclosed sampling accessory.
So I would say that if the sample probe is in an enclosed sampling accessory, I don't think there's too much worry about light that's surrounding the environment. I think the major concerns for those situations would be in a bioreactor that's uncovered, or there's extra light getting in there at different points of the day that might kind of skew the results. But there's also probes that are out there for the Procelix system that are actually reduce the light. So the way that they're built, it protects from light, and the goal is to minimize any effects of external light for the system. So.
Okay, thank you then, Alex. And Kim, is there anything you'd like to add here?
our company has two types of different probe, the regular probe and also the light reduction probe. So if you use the light reduction probe, it's probably will not a problem. And then if you use a enclosed, sample reactor, regular probe may not a problem, but you can check, testing the regular probe and then without, wrapping aluminum foil at the connection and then testing that again with aluminum foil to see if you see any different. That will tell you that if there's no difference, that will tell you that, there is no straight lines effect, no straight line concern that you need to worry about.
Okay, thank you, Kim. And Greg, is there anything you'd like to add to this answer?
I think Alex and Kim answered it pretty well. I would just add that stray light becomes more of a factor generally when you're starting to look at a bigger reactor, a bigger tank, where there's more potential avenues for stray light to enter. And it becomes more difficult to protect it from stray light.
Okay, great. Thank you for those answers. I'll move on to our next question and I'll ask this one to Kim. And this question says, could this system be used for direct process control? E.g., if a signal reaches a particular value, could the active adding a culture media component?
So first, in order to do real-time monitoring, you have to build a model. In order to do that, you need to collect your Raman signal, and you also need to, like Alex was saying, you also need to collect the offline measurement, and then do reference associate your offline measure with your Raman spectrum, and then build the model. After you build the model, you can test this model to see how well the model behave. And then, you can do that, multiple times, to get confidence that your model is good. Once you have confidence that your model, give very accurate prediction measurement, then, you can apply it, real time for process control. And then, because when you monitor real time, it will give you the measurement in real time. And then, you can use that real time measurement to make decisions about, adding buffer or adding whatever. So.
Okay, thank you, Kim. Greg, is there anything you'd like to add to this answer?
I can provide a specific example. So one of the most common applications for real-time control we see in the upstream space would be for a glucose control loop. So the Raman probe would communicate with the control software, say hypothetically Delta V over OPC UA, communicate with the regular interval, say every 15 minutes, what the glucose concentration is. And you can set up a control so that if the glucose it's below a certain concentration, it will trigger Delta V to activate one of its pumps to start pumping the glucose feed back into the bioreactor until the glucose level is above the minimum set point. So we see that being used fairly broadly for people that are trying to implement Raman.
Thank you, Greg. And Alex, is there anything you'd like to add to it?
Yeah, I was just to mention that with the OPC-UA connections, the certain tags like within the Raman can be dashboarded, and we actually currently have that in our lab where we have a dashboard that the Raman measurements are being uploaded to, and with that, you're able to, like kind of how Greg mentioned, set up pumps or set up some sort of control based on those softwares or based on those signals.
Okay, great. Thank you for those answers then. This next question will go to Greg, and it says, I saw one of your slides showed multiple probes in multiple reactors. Are those probes using a single model for prediction, or can they be operated independently to monitor different compounds?
So the probes, you can have up to 4 probes on a multi-channel unit, and they can all be loaded to measure different components. You can also you can select which components you want to measure. So if you have a list of 8 different components and you want to measure them across 4 reactors, you can do that. Or you can say, have 2 probes connected to an upstream step, 2 probes connected to a downstream step, measuring different components. The only caveat is the way that the multi-channel works is it can only be acquiring signal from 1 probe at a time. So you can acquire signal from all 4 probes at a time, but you can create a sequence for where you can decide which probe to select in which order. So if you have specific settings that have shorter integration times and need to be measured in sequence multiple times in a short period of time, you can have those alternate back and forth with the longer ones being at a broader interval, less frequent interval.
Okay, thank you then, Greg, for that answer. Alex, is there anything you'd like to add to this answer?
Yeah, I was gonna add that this is one of like I think one of the biggest advantages of the ProCellEx Raman is its capabilities with multiple probes that can all be operated using different models or the same models across different bioreactors, but it really allows a lot of versatility for this instrument, especially in intensified processing where you can set up sensing at different points, measuring either, the same component or various components. Obviously, like Greg mentioned, they kind of have to be done in a cycle, but it's pretty easy, especially based on the cables allow like pretty long extension across like a room or within like kind of a spread out area. So it really doesn't take up a lot of space. You're able to spread out the probes, and it's a pretty low. I would say it's a pretty low invasivity, or it's not a very invasive to like the process that's going on. So I think that's definitely a big advantage of the ProCellEx system.
Okay, thank you then, Alex. And Kim, is there anything you want to add as well?
I think Greg and Alex give a very good detail about our, 4-channel probe. I don't have anything to add.
Okay, thank you then. And this next question is for Alex. It says, is the integration time mentioned in Alex's slide the same as the Raman scan inquisition time, i.e., we are averaging over a longer duration for acquiring the wavelength intensities for 8 seconds versus 4 seconds?
Yeah, so the integration times are basically just the amount of time that the laser is focused on the sample, and it waits either the 4 seconds or 8 seconds to gather as much of that Raman scatter as possible, with the Raman scatter being a much less efficient technique than Rayleigh scatter. It requires these longer integration times. For the purpose of downstream and really driving down that total measurement time, we didn't do any of the extra averaging. So for instance, if you were to do like 5 averages at 8 seconds, it would take 5 separate 8-second scans, average those spectra together. But in that case, you're ending up with 8 times 5, so like 40 seconds in order to generate one single spectra. So we did some work previously that I didn't provide here, but I actually, in using these like downstream samples, I compared the the error and the RMSEP values for different levels of averaging. So I started with just doing no averaging, so just one single 8-second scan versus 10 averages, and there was not enough difference in those to really demand the need for higher averaging. And since we're obviously trying to drive down the integration time for these models, we just did no averaging. Obviously, the averaging theoretically increases the accuracy and robustness of the model, but that was kind of a sort of balance that we had to find. So for the 8-second integration time, that's just one 8 seconds per measurement. And then we also did 4 seconds, which just only focuses on the higher range. So at 4 seconds, we weren't worried about the lower concentrations that would provide too little of a signal. And at 4 seconds, we were still able to generate strong enough signal and good model evaluation results with a lower integration time.
Okay, thank you then, Alex, for that answer. And Kim, is there anything you'd like to add here?
No, I think, this is questions for Alex, so I don't have anything to add.
That's okay, don't worry about it. And Greg, is there anything you would like to add before the next question?
I would just add that the specific integration time for an individual step is always going to be a balance of how much signal you have versus how well you can view your individual components. So depending on your step, the integration time could be significantly different, but in most cases, a single spectra should be able to be acquired in usually about 30 seconds or less.
Mm-hmm. Yeah, I guess I can also add a little bit more to that. With these highly concentrated substances, the signal is obviously very strong compared to samples that might be at different steps of the downstream process. So I would imagine that in other chromatography steps where you're not really reaching, you have like a fairly clean sample at this point, and you're not reaching these high concentrations, that would require probably a little bit higher of an integration time. But still, the goal is to kind of choose a time that is providing enough signal, but not too long that it's not helping your implementation of Raman.
Okay, great. Thank you for your answers, Adam. This next question I'll ask to Kim. And this question says, how do you select the Raman laser wavelength that is specific for the molecule of your interest in the complex media?
So our ProSelect Raman analyzer has a 785 nanometer excitation wavelength. So you cannot select it. The excitation wavelength is set. So you can use this excitation wavelength, to test your molecule of interest to see if, and then play with the integration time to find a good enough signal. And then you can, collect the offline sample and then see if you can build a good model using your offline sample and your Raman spectrum.
Okay, thank you, then, Kim. And Greg, is there anything you want to add here?
Yeah, I would add that if you're asking specifically about a molecule of interest, what we're trying to identify is what peaks along the Raman shift are most critical to be associated with your specific component. So depending on how novel the component is, there are a lot of resources out there that can give you guidelines about what specific shifts are most relevant for specific components, because the nice thing about Raman is no matter what other components are in a specific medium, the peaks for each component is going to be the same. The only thing that's going to vary is the intensity and how visible it is within the specific background matrix. So you can refine the peaks of interest to be very specific to each component you're trying to measure. So if there aren't relevant references for what you're trying to measure, we're obviously going to help you refine, identify them. But another key approach is getting as pure a sample of the specific component as possible as a good baseline measurement for where the critical peaks are.
Okay, thank you then, Greg. And Alex, is there anything you want to add here?
I don't have much to add for this specific question.
Okay, then. That's fine. Thank you for those answers. This next question I'll ask to Greg. It says, if we want to use Raman spectroscopy to measure multiple components at the same time in the cell culture broth, does it require multiple probes?
At a baseline, the answer is no. You can use one probe to measure multiple components. You would build a model for each specific component of interest, and then the same probe and the same analyzer would be measuring all the components at the same time and creating or giving you those measurements in real time. The one caveat is when you're building that initial calibration model, the integration time for all the components will be the same. So you'd be getting all the different measurements at the same, for all the different components at the same frequency.
Okay, thank you, Greg. Alex, is there anything you want to add here?
No, I think that covers it. You're able to select multiple models for different components and apply them on the same. We do that often with our upstream ones with titer, glucose, lactate, all being measured within the same bioreactor with the same probe.
Okay, thank you, Alex. And Kim, anything you want to add here?
Yeah, I just want to add that, our analyzer allow you to upload multiple model if you just use a single probe. And then it's also give you the real-time concentration displays, on the Raman analyzer at the same time. So you can use, different component that you are looking for at the same time. So it helps you to make the decision real time.
Okay, thank you, Kim. Great. So I'll move on to our next question then, and I'll ask this question to Alex. This question says, for aggregate analysis, how accurate is Raman, and any models do you have or data where aggregate content is analyzed correctly?
Yes, so that's a good question. We do have models for HMW. I don't think they're really necessarily at a point where it's generic, but it's something that we are working on. And some preliminary figures, HMWs are predicted correctly within 15% accuracy. So it's definitely not as accurate as measuring just protein concentration or some other components, but it's definitely in the works. There's definitely a capability for that, as well as other downstream impurities. So this is definitely something that's being worked on, something that's possible, and we'll be kind of putting out new information shortly.
Okay, thank you then, Alex. Kim, is there anything you want to add here?
Yes, we are working on this. One thing I want to add is that for some process, the amount of aggregation can be really low. So it might be a challenge for that.
Okay, thank you, Kim. And Greg, is there anything you want to add here?
I don't have anything to add.
That's okay. Thank you then. This next question to Kim says, Does Raman spectroscopy require initial calibration with reference material for measurement?
So for our software package, we have two different statistical software. One is PCA, which is Principal Component Analysis, which allow you to do data qualitatively. And then the other statistical software that we have is called Partial Least Square Analysis. And this software allow you to predict the value real-time quantitatively. But in order to do this, in order to do the partial least square analysis, you have to build a model. That means that you have to set up system, collect the Raman spectrum, and then you also need to measure the sample offline. And then from this, you can build a model. So it depends on because I know that some process they don't have a way to measure the sample offline. So the only thing they can do is do principal component analysis, where you can outline your process, outline some of the sample in your process. But the ideal situation is where you can quantitatively monitoring your process by doing partial least square analysis. But you need, in order to do this, you need to have a method where you can measure the offline.
Okay, thank you, Kim, for that answer. Greg, is there anything you want to add to this answer?
Yeah, I would just add that for specific components, like the ones Alex mentions in the upstream space, glucose, lactate, protein titer, we do have methodologies in place, depending on the medium, to have a more plug-and-play solution. And generally for those components, we do have methodologies in place where we can calibrate to our historical data for those specific components and require significantly less initial data to do calibration. So that it's generally can be specific to the component that you're trying to measure. But we're constantly trying to improve how quickly someone can get that initial calibration batch completed.
Okay, thank you, Greg. And Alex, is there anything you want to add here?
No, I think it's been well covered.
Great, thank you then. And moving on to our next question, I'll ask this one to Greg. This question says, in addition to the protein titer, what are the main parameters that ProCellEx Raman could help monitored in DFB and new modalities, typically HCP, aggregates, HMW/.
I don't think these are done. I don't know.
Yeah, so a lot of the specific components we've already talked about in previous questions. I would just add that when you're looking at chromatography, measuring your illusion, definitely potential depending on what your components of interest are, what your residence time is, how fast you're trying to collect fractions. You can capture some of that key product information. And then, new modalities are always exciting for me. One that I'm specifically been excited about recently is the possibilities for Raman to be applied for mRNA and lipid nanoparticles. We already see there's multiple steps within those processes. I would call it specifically in vitro transcription as one that we know that Raman is well positioned to sort of tackle and be able to monitor mRNA concentrations as well as other TB concentrations. So definitely we continue to eye those new modalities as potential fits. And we have seen success in those areas.
Okay, thank you, Greg. And Alex, anything you want to add here?
Yeah, I can speak to this as well. So while my presentation, or my portion was kind of focused on just like the high concentration protein quantification. We also, the Millipore team has also been working on other components in the downstream space. So recently, it wasn't my work, it was our extended team's work, but they were able to monitor a few different components in a Pro-A chromatography step. So they were able to monitor just the protein concentration at a 98% accuracy, the monomer concentration at 97% accuracy, and then looking into other impurities like HCP at 90% accuracy, and then aggregation HMWs at, like I mentioned kind of before, 85% accuracy. So there's definitely the capability for Raman to measure these things, and the more we look into it, the more calibration data we're able to build these models with, the more accurate those should be. So
Yeah, that was actually
very versatile tool, the Procellus Raman instrument.
Yeah. One of our cells down
thank you.
one of the things.
And Kim, is there anything you want to add here?
We are always welcome new collaboration. So if you have, new modalities, and good that you like to monitor, you are welcome to contact us, and then we can set up a collaboration.
Okay, great. Thank you for those answers. This next question, I'll ask this one to Kim. It says, what are the challenges when measuring using this system in high concentration MAB during TFF?
So for high concentration, I think the challenges are you have to, I guess, optimize the integration time. So you want to collect data, but at the same time, you don't want oversaturated signal. Like, Alex was presenting in his slide, you can see that, for low MAP protein concentration, he was using 8-second integration time. And then for high MAP concentration, he's reduced the integration time to 4 seconds. So, that's something that you need to keep in mind with when you, go with high MAP concentration.
I can add to that also. I think initially some of the challenges that I thought would be more challenging was the actual idea that differences in the formulation or buffer background will cause more error in the readings. That wasn't really the case for the high concentration samples, just due to the fact that the signal from the MAB was like overpowered any of those smaller buffer signals. I would imagine that if there was a decrease in the amount of protein, or there was other background signals in there that were making more of an impact, that would be somewhat of a challenge. But that was kind of a pleasant surprise throughout this process, that with the generic capabilities of that high concentration model, was that it was pretty independent of the buffer background. There's not really going to be, I would imagine, much of a standard buffer background that would be able to overpower the signal from upwards of 250 grams per liter of protein. But yeah, I mean, like Kim mentioned, the major challenges is, I guess, just how you want to address your process, how you want to optimize the integration times surrounding your process. If you're looking to go upwards of 300 grams per liter or even higher, that's definitely a capability, but would include having to lower that integration time, and then you're losing the bottom or the lower concentrations that the signal just wouldn't be strong enough to measure anything. But if you're going up to those And sometimes you don't really need to worry about those lower concentration ranges. It's not going to be something that your process is controlled around. The higher concentrations would probably be the focus.
Thank you, Alex. And Greg, is there anything you want to add as well?
Nothing to add on that one. I think it was responded to well.
Okay then, well, that was our last question for today's Q&A session. So I'd like to thank everyone who sent in their questions and to remind you all that you can watch this webinar and other webinars by going to our website, which is biopharmawebinars.com/webinars. And before we finish today, I'd just like to go around the table here and ask our presenters if they have any concluding remarks or takeaway comments. So we can go in order of presentation. Greg, over to you first.
Yeah, I would just summarize that we've seen that TFF and Raman spectroscopy can be a powerful tool when leveraged together. And we're happy to work with any and all who are interested in exploring it more and implementing it more in their process.
Great, thank you, Greg. And Kim, over to you.
So our ProSelect Raman's analyzer is a very powerful PAT tool, especially for downstream process where you need to monitor residual or impurity clearance. Because I saw that some of the process where they was not able to, they was collecting the offline data, but they were not able to monitor the process real time. So when they actually run the offline sample, they saw a really high, such big increase of some of the sample. But if you are able to use ProSelect Raman for real-time monitoring, you can able to see that right away without, waiting days or hours before you can see the result. And then, that by being able to monitor the process real time, you can make the decision real time or maybe change the process. So that way you don't have, I guess, out spec, what we call that, out spec for your final product.
Yep, okay. Thank you, Kim. And Alex, over to you.
Yeah, I just wanted to, again, touch upon the flexibility of the ProSelect Raman analyzer. So not only are you able to use multiple models to predict component or predict the quantities of different components in a sample, especially across the 4 separate channels. But you also have multiple different implementation techniques. So you can use it as an at-line instrument with just like kind of a single sample cap that screws on, or you can submerge it into a bioreactor or a surge vessel, like a brake tank, or with the flow cell and have like actual inline monitoring. So I just think it's a very versatile tool, and it definitely has many advantages over some traditional sort of monitoring tools.
Okay, thank you, Alex. And once again, I'd like to take this opportunity to thank our presenters for joining us today. And that was Greg Voiter, Senior Engineer, Upstream Process Development at Merck. Also, Dr. Kim Nguyen, Senior Scientist, ADC Bioconjugation Template Innovation at Merck. And also Alexander Faris, Bioprocessing Engineer at Merck. Thank you, Greg, Kim, and Alex for joining me today. It was a great webinar. And hope you have a great rest of your day. Take care now.
Thank you. Bye.
Thank you.